What I'd like to do is go through a very brief idea of how I think the electric universe works. I'd like people to question me, but preferably not all the way through, because we could just end up going for several hours. Some people may have done their homework and be fully ready with all the debunking sites, and I haven't got answers for all them, but if we can sort of spread out the questions, preferably near the end, but this is how we go. So I just want to give a very basic understanding of the electric universe and to challenge all the assumptions that we've come along here with. So most of us probably had some education in the way the standard model works, so I just want you to sort of leave them behind and just accept that there's another possibility, as all science does have. There is always a second possibility, at least a second possibility. So a few words just describing it, a new paradigm based on new observations about the role of electricity in space and in nature as a whole, not just in space but right down to cellular level. It's a holistic model. Okay, so the guy who's driving it at the moment believes that it spans many disciplines and is a big picture. It's not just a narrow field of study. Highlights in electrical patterns wherever we go. Enables lab experiments, so we can actually see things happening in space and in the laboratory which can be reproduced. It provides answers to problems not clothed in metaphysics or mysticism, which is possibly what I believe some of our body science is in. Multidisciplinary, I'll keep emphasizing this, multidisciplinary and more inclusive of information from all science. And it points to practical possibilities. So it spins off into all sorts of directions once it's been given perhaps a little bit more money to get into different subjects. Okay, I thought, and Martin's suggestion, that I'd put in some really odd questions and spring some ideas from them. For instance, how could the dinosaurs survive in our current world? The sizes we're finding that they did exist, how could they possibly stand in our gravity level? How could they fly in our current situation? I believe that it is absolutely impossible for them to exist in this current gravity, so possibly gravity was lower. Okay, gravity may not be a fixed standard. Yeah, something like that.
Wasn't the Earth thicker instead of the gravity lower?
Yes. I'm suggesting that gravity isn't a fixed standard constant, but is a variable. Okay. Okay. We'll get on to that a bit more. What about in coal? Has anyone come across these artifacts which have been found in coal? No? Well, how do we believe coal was formed? How long did it take? How many millions of years did it take to form? When we can find human artifacts buried hundreds of feet into thick seams of coal, and other things as well. This iron pot was found in 1912 in a coal mine somewhere. In Virginia, they found this. And there are hundreds of other examples of human artifacts, pieces of the human body, all sorts of things trapped in solid coal. Okay, so is coal a more recent structure than we can imagine? This chap is Gerald Pollack. Anyone heard of Gerald Pollack? Anyone study biology or water? His team in Washington University are looking at ordered water, and it is a slightly electrical subject. It's a fourth phase of water he's discovered. Another little experiment he does is with, it's obviously not going to work on this. Yeah, some of the slides are not working because of my dear friend's laptop. That's supposed to be a water bridge between two beakers of water at 25,000 volts. It actually forms a bridge between two beakers. Has anyone seen that? It's an interesting little subject. Here's another one. Going back into ancient history, there was a calendar of 304 days, according to Romulus. When the Romans, did they miscalculate? Only 10 months. As you might see, we started on March, ended in December, Decem being the 10th month. So that they blamed that on Romulus. He was pretty bad at maths, or was it really only 300 days in 753 BC? Okay. Anyone recognise this? We have over here a vortex from a typical hurricane. Anyone know where that vortex is? Come on, these space watchers. That's the North Pole of Saturn, isn't it? That's Saturn's North Pole, and you can see the shape. It's quite similar to the shapes you find in other objects. Is this vortex just a mechanical thing, or is it an electrical thing? Another question. Up there is the sort of typical view you see of Mars, a little blurry dot, even in the best telescopes. So how did these guys, the Blackfoot Indians, call Mars Starface? They actually knew that Mars had a huge scar on his face. And we didn't know until 1972. That's the first time we saw the image of a scar on Mars. So why did they know that? And another one. This guy is Dr. Anthony Pratt. He works out in Arizona, nuclear physicist working for the government, and he's been generating these enormous explosions in sparked plasma discharges. Has anyone seen that shape before? That's a typical spark discharge with a little piece of wire which has been high voltage melted, and it forms this beautiful shape. Somebody obviously saw this before, 8,000 years ago, because people drew this on rock, basalt rock. They also drew it in just about every other country in the world, and all their own versions of it. Some of them look quite sexual, but mostly they're fairly innocuous. But these guys saw something. It was in the sky long enough for them to actually sit there and chisel it in rock, and then you can find it in just about every country in the world. And even now, the traditions of the Kananga, I think it's the Dugong tribe in Africa, they still make these masks, which are exactly, or the head masks, which are just the same shape. Somebody has actually got a very deep memory from this occasion. Okay. And again, the last one, the question about the way the sun behaves. So we all know the sun is a nuclear fusion model. It's constant heat generated by helium and hydrogen and all this stuff. But it varies over a period of 10 years. That is the X-ray output of the sun. It varies quite considerably, and we all know that the solar cycle goes up and down every 11 years. There's a lot of variations in the sun which aren't explained by the standard model.
Do other stars do the same thing?
Probably.
Probably?
Yeah, but we're not
Has
close
anyone
enough to
checked?
actually see the detail. Sorry?
Has anyone checked? I mean,
Yeah, well, most stars are variable. Very few stars are fixed. Most stars are very variable.
variable in terms of...
Various things. Colour, brightness, and magnetic field X-ray output and so on.
Colour in particular, they're
Yeah.
normally very consistent on. We use that to identify individual
Yes,
stars. It's
yes.
like a
Yes, our Hertz-Russell diagram tells us
Yeah.
just how old they are, doesn't it?
And what
We
they're
believe
made of.
that. We believe that the age of the star is decided by its colour, because they go through a phase of changing colour over billions of years.
Not quite. We believe the composition of the star is gives it its colour.
Yeah,
And normally the composition is an indication of its age.
yeah,
Like something that's had time to convert a whole lot of hydrogen into helium,
yeah, yeah,
has a certain amount of
yeah,
helium.
yeah.
That gives you a...
Has anyone actually seen it change from one phase to the other?
In a human lifetime, no.
Well then, how do we know it changes? How do we know your theory works?
Suddenly it's my theory.
Yes, yours.
I'm a question.
I'm blaming you. Right. There are competing theories, and I'm just going to go through the two basic theories that have gone through history from the ancient Greeks probably onwards. Cosmology has always been studied as the queen of the sciences, and competing philosophies have mainly fallen down on the two sides, the empirical side and the deductive side. In other words, the observational physical measurements and the mathematical elegant theories, which we are in at the moment. We're in the elegant theories rather than the observational theories. Okay, so one of the earliest guys who had a philosophy about the universe, or the way the solar system worked, was René Descartes. Sorry, is it Descartes? Not Descartes. He had a vortex theory about the way the planets worked their way around the sun, and he printed it in his little book. And he had his vision of this big equatorial whirl. And so he saw the link between the sun and the planets was a varying by this equatorial whirl. NASA discovered the equatorial whirl in the form of the solar wind, which actually does perform these spiral whirls. They call it the heliospheric current sheet. Okay. Do you want to say a word? So I'll read it.
Oh, beyond my area here.
Okay. It's beyond my area.
I'm
I'm electronics, I'm totally area. It's not my area at all, so you'll soon find out I don't know a lot of people about this. The other guy, obviously, who was about the same time, 1630s, was Isaac Newton. He came up with his theory of gravity, and that became the law that we still observe now. And forces going in pairs. Gravity is the overriding control of the whole solar system and the universe. And obviously Einstein had to improve on it with his various theories. But is that necessarily the only way? Okay. Towards the end of the 19th century, it's politically correct to become more of a gradualism theory instead of the catastrophic theories that preceded it. So a lot of things became very gradual. Evolution took off because it took millions of years to change things, and things didn't happen suddenly. And a guy called James Sutton decided the present is the key to the past. So what happens now mustn't happen in the past, and nothing in the past has ever happened that doesn't happen now. Okay, which is very nice and helpful because things have been very steady for the last 500 years. Things have hardly changed. And so it became easy to mathematically model the way the thing works because it works very gradually. And, well, a lot of subjects, I think. Electromagnetism tended to be pushed out and gravity took over as the main driving force. I don't know anything about special relativity, but that was about 1905, and then general relativity followed up to about 1915 when they finally zapped it. Okay. So, currently accepted is the standard model. As far as I'm concerned, it's all about uniformity, it's only interested in gravity, it's very maths-based, largely untestable, unless we can have a really, really big hadron collider which will find even the smallest particle, and it's treated as fact. If you go to school, you are expected to learn the facts. And I don't think the experiments that are being done at the moment are anything like going to find what the truth is. And of course we've got these lovely people like Ryan Fox who tell us all about it in their beautiful way on the media. So we've ended up with a universe a bit like this, with this tiny little bit down here that we actually know anything about, and the rest of it is totally invisible and untestable and will never be known about probably. So, as my friend I met the other day, a nuclear physicist, said, it's the proposal. We don't have to believe it. It's just a proposal.
Like the rest of physics.
Exactly. It should be, and it should be trusted to be factual. So, what physics goes behind the electric universe? How long have I got?
10 minutes.
What? 10 minutes? That's not long enough. The electric universe starts with what we can see and test in the laboratory. So it's totally scalable, and it can be used to describe anything from the cellular level up to the super cluster level. And it doesn't require any black art or imaginary entities, and we can actually say, what are the four states of matter? Sorry, what are the three states of matter? Oh, give it away. What are the states of matter that other people understand?
Plasma.
Plasma, yes, plasma, that's the important one. Plasma is the fourth state of matter, which we're not normally talking much about, as I understand it at school nowadays. And so plasma for me is the important thing. And a typical atom of hydrogen, got one proton, one electron. We all know this stuff, it's not new to anybody. And we can actually split them apart with a bit of energy. It could be either heat or electricity. And then what do we end up with? A bit of radiation.
Depends which one you hit with the energy.
Oh, come on. We split the atom apart and we've got an ion and an electron, haven't we? Yeah, that's the basic system in a plasma.
It depends which bit of it you're trying to split apart. If you actually split apart the nucleus, you end up with other bits of protons.
No, this is just normal run of affairs.
You can't actually guarantee where it's going to split.
All right,
There is
you're going to commit too fine. Don't think you're going to commit too small there.
Unless you've got a statistical sample across about 10,000 atoms, you don't really have a...
Yeah. We're normally dealing with a lot of atoms, not a small number. So if I was saying what is the majority of the universe, I'd say that plasma forms the vast majority of the universe. Gas a little bit like on the small side, liquid even smaller, and solid even microscopically smaller on the universe side. Anyone know what proportion of the observable universe is plasma?
My understanding is that plasma is generally above 10,000 degrees Kelvin, and about 99% of the universe is below that.
So 99.995% of the universe is plasma. Thank you very much. That's well supported there. Yes.
I was actually saying the other way around.
Yes.
Could you say that 99.999% of the universe is empty and therefore...
It's very low density plasma, yes. So it's dissociated charges of positive and negative.
Right.
Ions and electrons.
What criteria are you using to identify a plasma?
What Hannes Alfvén said.
Which
This is
is...
his statement. He's a Nobel Prize winner. I'm not going to...
I'm not familiar with what he said.
All right, that's his statement. That's his statement. 99.9%.
The Nobel Prize winners
Yeah.
did exactly the opposite.
Yeah. Okay.
So
Well,
you
stick
can't
with
really crack that.
stick with this guy. He's the father of cosmology.
I'm
So
pretty
I'd
sure
say
Einstein
that
won
most of the
a Nobel
universe.
Prize as well.
Most of the universe is plasma, so we should be studying plasma as being the important part of the universe, and the little bit that we live on, that little tiny little layer that we live on, is pretty minuscule, and that's what we base all our interest in physics on, what we can see on the Earth's surface. All right, so we should be thinking outside of that. My flip chart is meant to be telling me what the different forms of plasma are, but I'm not sure if we've got time for that. Can I see if anybody has any ideas what forms of plasma there are?
I'm all ears.
Cold plasma, hot plasma?
Right. Right, let's think in terms of things that happen on the everyday front. Well, not necessarily every day, but in the weather front. Just went out and look outside when there's a thunderstorm. Lightning, good, excellent. So lightning is one, all right. Okay, any others?
The kind you have in a glass ball?
Yeah. Okay, that's plasma ball. Yes, that's another one. Yeah. I was going to bring mine along, but I couldn't fit it in my bag.
Semiconductor manufacturing.
Yes, there you. Were you two talking last time? Semicon. All right. Yeah, that's another one. It's good. I've got a whole thick 50 pages of semiconductor manufacture. Yeah.
This is uses.
Hmm?
Surely this is uses as opposed to actual different types of plasma.
These are common experiences of plasma. Yeah. So just to see how you.
Planes.
Planes. Yeah, planes are borderline between. This is arc mode here, and that's glow mode. So.
Plasma inside of the sun or star?
Yeah. That's good. The sun. Yeah, so flame is, I think, down here. Any others?
TV sets.
TV plasma.
Plasma TVs.
Yeah, that works on ARC, yeah. They've actually discontinued. They closed the factory in 2013. And that's where all my slides came from that plasma factory. Yeah. It was a thing of the past now. Any others?
Boiling salt?
Pardon?
Boiling salt?
Yes, I'm not quite sure about that. Can I mention sparks?
Well,
I mean, sparks might be up there.
Boiling salt doesn't give you a spark or an arc or a glow, but it is still technically an ionised solution.
Okay. Come on, what do you see in the North Pole? Those beautiful...
The aurora borealis.
The auroras, yes.
That's not a plasma either. That's
Yes, there's a
that's an
plasma.
optical effect.
Yes, it's an energised gas, which is a plasma, isn't it?
The gas itself is not energised, it's the photons passing through it which
I had one guy in this last lecture.
This is a
We carried on an email for a while.
If you want me to
Yeah,
shut
there's a whole
up, just say so.
All right, thank you.
I'm going to sit down and be quiet.
It's all right, I only have 20 minutes this time. So, just a resume of that. We've got the arc mode, the projector lamps, and semiconductors, and so on. And the surface of the sun is a very good example of a plasma. Glow mode, we've got the aurora, we've got fluorescent tubes, yeah, and the little CFL bulbs, which I've got to bring as well, and flames, which I've got in the arms. Okay, you can see there is a dark mode here, and then obviously there's a glow and an arc mode further up. Anyone seen how a fluorescent tube works?
Yes.
Or even these little lights? No, not these ones. So all you need is a spark to start it going, do you, or some form of burst of energy. And once you've got it energized and ionized, once the gas is actually conducting, then you can maintain that energy with quite a low current, hence they're quite economical. But it's the ultraviolet light that's actually giving us the effect of light by making the phosphors glow, isn't it? So ultraviolet light is a very common result of a plasma discharge. Yep, it's quite economical, isn't it? Terrible light, but it's economical. So my idea of the electric plasma, how long have we got?
10 minutes.
Thank you, you're very generous. We have a pulse of energy to start us off. We're ionized into electrons and ions. The electrons and ions can move around, and we tend to have to maintain it with some form of energy. And in my thought, electricity is a very good source of energy to maintain the plasma. The star obviously is in the arc mode. My suggestion is that the star is actually supplied by an electric current from the galaxy. The glow mode, well, we can see the solar wind piercing through the magnetic field of the world. Dark mode, we don't see very much of because it's invisible, is how most electricity is conducted through the universe, between all the galaxies and various objects which we see up there. Tends to form in plasma filaments. Anyone seen a plasma filament before? Right. As current passes along through space, it will actually form into tight filaments. They tend to twist together. Hence, I brought my modelling balloons to become plasma filaments. This will probably blow up on the time I try and do it. But if you think about it, as they go along, they actually tend to twist together and form into a spiral shape like that. Hence, we've got the magnetic fields binding them together as the current flows through longitudinally. And they bind themselves together very well. So that's nature's natural way of conducting electricity through space. There's the aurora. Tristan Berkjon was one guy who actually went out and observed the auroras physically with test equipment. He measured the currents, deflections of magnetic fields, and he obviously saw what was going on there, that this is electricity coming from the sun. And so he built his Torella in the laboratory. He showed that a magnetic field here, high voltage, you can generate everything that you see on the sun. And his experiments are still seen these days as being a landmark. Obviously, our mathematicians in Britain said, no way, this is not mathematically good, and he denied him any chance of publishing his book in England. And not until the 1960s then they realised he was right all along. So the spaceships proved that there was high-speed particles coming through the atmosphere, and he went to his death. He actually committed suicide, we think, because he was so desperate at the end. But he was a good chap. He did try desperately to get everybody to listen to him. He went on with the subject, and he was a Swedish engineer who became a physicist, engaged in this sort of study, and he thought that, as I said before, these complex filaments spread out throughout the whole of the universe. And we've seen photographs like this which show these plasma filaments interconnecting across space. Unfortunately, very early on in his career, he talked about magnetohydrodynamics. Anyone read about that? And that said that there's no way we could have conduction in space because plasma is a pure conductor. Absolutely zero resistance. Which, unfortunately, was wrong, he realised, And he actually spoke out at his Nobel Prize ceremony. The plasma is not actually understanding how beautiful these theories are because it refuses to obey them. Because he knew from that point, a long time before that, that there was no way that we couldn't have electric current in space. Plasma is not a perfect conductor. So we can have voltage difference, we can have currents flowing through space, and it is quite possible for it to exist in the real world. This guy carried on, Tony Peratt. He came over to UK in 2005. I actually filmed him talking about a very interesting subject about those petroglyphs. He produced a nice little video which doesn't actually run now. We did try, which was a supercomputer generation just using simple equations of two spiral galaxy profiles. And he actually produced that in a supercomputer at Los Alamos. This guy did it with physical pieces of wire, and he actually set them off as a plasma discharge. As you can see, they twist together and they look just like the form of a spiral galaxy. He did this in 1956, and he also believed that what keeps our galaxies rotating is more of a homopolar action rather than a dark matter and black hole and dark energy action. And if you think about it, that's what's inside your electricity meter. The simplest core motor is just a disk, magnetic field, electric current, and it spins. It's the simplest form of motor you can get. And he believes that's what is the way that most of our planets and stars work on.
Not inertia.
Not inertia. Well, inertia is a very small part of it. The main thing that's maintaining it is the electric force that's keeping it going. There's obviously a bit of mechanical inertia in there. Yes, so if anybody's looked into Faraday's homopole motor, you probably know all this anyway. I'm running down. This is probably going to be one of the last slides, I think, at this rate. This is a grand picture of what the electric universe guys believe is the way the planets and the stars all work into a system whereby in space electricity falls through these giant invisible filaments, and as they get close together and form into our spirals, then they gradually twist together and form into these galactic shapes. If you look at this point, they call this the Z-pinch point, where they tend to twist together. You get a real hot spot there. And it's quite similar to if you have a star. Star tends to form in one of these conduction panels at a Z-pinch point like that. So a star will actually be at a point where a filament is actually twisted. And we'll see a picture of that in a minute, if I can find it. Here we go. This is one of the things that we got from our Los Alamos experiments.